A red-black tree is a binary search tree that keeps itself balanced using one extra bit of information. Each node is colored red or black. The problem is that a normal binary search tree can become a chain. If we insert sorted keys, search can degrade from logarithmic time to linear time. A red-black tree keeps the same binary search tree order, but adds color rules so the tree cannot become too tall. The color rules are the guardrails. The root is black, a red node cannot have a red child, and every path down to a leaf has the same black height. When an insertion breaks those rules, the tree repairs itself with recoloring and rotations. The goal is not perfect balance, but good enough balance. That is why red-black trees give search, insert, and delete in logarithmic time, while still updating quickly. The first rule is simple: every real node is either red or black. The color is part of the data structure, not the key order. The root is always black. If an operation makes it red temporarily, we repaint it black at the end. Every missing child is treated as a black nil leaf. These nil leaves matter when we count black height. A red node cannot have a red parent or a red child. This prevents long chains of red nodes from stacking up. Finally, every path from a node down to a nil leaf must contain the same number of black nodes. This is the black height rule. Together, these rules keep the tree close enough to balanced while preserving the binary search tree ordering. Now connect the rules to balance. Same black height means every root to leaf path has the same number of black nodes. A short path may be mostly black. A longer path can insert red nodes, but only between black nodes. Because red-red is forbidden, red nodes cannot stack into a long chain. Between two black nodes, there can be at most one red node. So the longest path is at most about twice the shortest black-only path. That is the core reason the height stays logarithmic. A red-black tree is not perfectly balanced like a complete tree. It is balanced enough to keep search, insert, and delete efficient. Before we use rotations inside red-black trees, let's understand the move by itself. A rotation changes shape locally, but keeps the binary search tree order intact. A rotation is a small local rewrite. It changes parent-child links, but it does not change the binary search tree order. In a left rotation, X moves down to the left, Y moves up, and Y's left subtree becomes X's right subtree. The order is still the same: everything in A is less than X, then B sits between X and Y, and C is greater than Y. A right rotation is the mirror image. Y moves down to the right, X moves up, and X's right subtree becomes Y's left subtree. Red-black trees use rotations after insertions or deletions to repair shape, while recoloring repairs colors. Before we repair red-black tree insertions, separate the process into two parts. First, insert by normal binary search tree order. Then, if a color rule breaks, fix it. Insertion starts exactly like a normal binary search tree insert. The colors do not affect the search path. For key 1, compare with 20, then 10, then 5. Each comparison chooses left or right by ordinary BST order. When we find the empty child position, we attach the new node there. The new node is colored red. Why red? A red leaf does not add to the black count on any path. If we inserted it as black, one path would immediately get an extra black node. But red can create one local problem: a red parent with a red child. The next step, insert fix up, repairs exactly this kind of violation. We continue from the inserted red node. The only broken rule is local: node 1 is red, and its parent 5 is also red. Look at the parent, the uncle, and the grandparent. Here, parent 5 and uncle 15 are both red. When the uncle is red, we recolor parent and uncle to black, and recolor the grandparent to red. This preserves the black count below the grandparent. The possible red-red problem moves upward to the grandparent. In this example, 20 is black, so the loop stops. As the last step, we make sure the root is black. Now compare the other important case. If the uncle is black, recoloring alone cannot remove the red-red chain. For this same side shape, rotate at the grandparent. Then recolor the new local root black and the old grandparent red. So insert fix-up has two tools, red uncle means recolor, black uncle means rotate and recolor. At the end, force the root black. One final detail, the uncle can be a nil leaf. Since NIL leaves are black, that is handled by the black uncle case. Deletion starts like ordinary binary search tree deletion. Find the key, and if needed swap with its successor so the actual removed node is simple. If the removed node is red, deletion is easy. A red leaf does not contribute to black height, so the red-black rules stay intact. The hard case is removing a black node. That path loses one black node, so black height no longer matches the sibling side. We often describe this missing black as double black on the replacement child or nil leaf. It is a marker for a black height deficit. Delete fix-up moves or removes that deficit using the sibling, recoloring, and sometimes rotations. We will keep deletion at this conceptual level here. Full red-black deletion fix-up deserves its own dedicated walkthrough. Red-black trees keep height logarithmic, so search, insert, and delete each take O, log n, time in the worst case. The tree stores n nodes, while iterative operations use O, 1, extra working space. Search receives the root and the key we want to find. As long as the current node is real and the key is not found, keep walking. If the key is smaller, go to the left child. If the key is larger, go to the right child. When the loop stops, return the node we found, or nil if the key is absent. Insertion receives the root and the new key. Create the new node as red. This avoids adding black height immediately. Walk down the tree exactly like a normal binary search tree insert. Use key comparisons to choose left or right until a nil child is reached. Attach the new red node at that empty child position. Then call insert fix-up to repair any color rule violation. Return the possibly updated root. Insert fix-up receives the root and the newly inserted red node. The loop runs only while Z has a red parent. First identify the uncle on the other side of the grandparent. If the uncle is red, we use the recoloring case. Recolor parent and uncle black. Recolor the grandparent red. Move Z up to the grandparent and continue checking upward. Otherwise, the uncle is black, including the nil uncle case. If the shape is bent, rotate at the parent to turn it into a straight line case. Then rotate at the grandparent. Recolor the new local root black. Recolor the old grandparent red. Finally, force the root to black.